Hi, this is John Whitaker for the graduate level probability class, and this is our, I believe, our 27th video lecture. And today we want to talk about the compound random variable. Essentially, I'm going to prove three facts today. One of them is the compound random variable identity. Then I'm going to prove a corollary to that, and then I'm going to have a fact that will be useful, especially in dealing with the corollary. In terms of looking at some examples for that corollary. So let us go ahead and get started, and what we're going to do to begin is we are going to recall what a compound random variable is. So as a definition, if we let x1, x2, continuing on, be a sequence of independent and identically distributed random variables. Then we let n be a non-negative integer value random variable that is independent of the sequence of x1, x2, forever, then S sub n equaling the sum as I runs from 1 to n of x sub I is a compound random variable. Okay, that was our definition. And I would like to add something to this definition. And essentially in this recall definition, I'm not so sure that I've been so explicit before about n being a non-negative integer value random variable. So here, in this non-negative, that means that n could be 0. And so what I'm going to do is say, in this setting, we define, so this is part of the definition, S sub 0 to be equal to 0. Okay. Now, here is new material, let's not recall, and so a new definition is in a compound random variable. Okay. The distribution of n is called the compound distribution. Or compounding distribution. So that's what it's called, compounding distribution. Okay. Well, here's a proposition, and it is the compound random variable identity. Here's what it says. It says, let m be a random variable that is independent of the sequence of random variables x1, x2, forever, because that forms a compound random variable. Okay, so M is independent of these guys, of this sequence. And M satisfies the probability that M is equal to N is equal to N times the probability that N equals to N over the expected value of N. Okay, where N is the index, an index for the compound random variable. And so N here can be equal to 1, 2, 3, forever. Then, for any function h, what we have is the expected value of S sub n times h of S sub n will be equal to the expected value of x sub 1 times, the expected value of n times the expected value of x sub 1 times h of S sub n. S sub m, so the wrong thing, it should be m. Okay, so that's the compound random variable identity. That's what we want to prove. And so we'll prove this by condition. So here's starting to prove. Okay, so we'll look at this. Well, note the expected value of S sub n times h of S sub n. Well, that's equal to, first of all, its expected value. S of n is the compound random variable. It is a sum, if you will, as I runs from 1 to n of x sub I and times h of S sub n. Okay? And so what we'll do is we'll compute this expected value by doing conditioning. And we'll condition based on what n is. Big N. Okay, so this is equal to, so doing this conditioning, so it's expected value of the expected value of the sum as I runs from 1 to big M of x sub I times h of S of n, given n equals to n. So that's a fact that we've proven before, and then this will be equal to the sum over all n values, so here n can run from 0 to infinity, of this quantity, the expected value, the conditional expected value. The sum as I run from 1 to big N of x sub I, h of s sub n, given n equals to n, times the probability that big N equals to little n. Now that is equal to the sum as n runs from 0 to infinity of the expected value of, well, here we know that n is equal to little n, so we might as well replace that here. So it's the sum as I runs from 1 to little n of x sub I, h of s of n, given n equals to little n, times the probability that n equals to little n. And now, what we know is that n is independent of the x sub i's. Okay. So this is equal to the sum, as n runs from 0 to infinity, of the expected value of the sum, as I runs from 1 to n, of x sub I, h, s of n, and that's it, times the probability that n is equal to n. And finally, the expected value of a sum is equal to the sum of expected values, so it's the sum as n runs from 0 to infinity, of the sum as I runs from 1 to n of x sub I, expected value of x sub I, h of s sub n, times the probability n equals to n. Okay, and here's what I want to tell you. I'm going to show this, but the expected value of any of these indexes, x sub 1 or x sub 2, h of s of n, they're going to be the same because they're the identically distributed nature and the independence here of x. So I'm going to show that. Okay. So, let me write this down. Now, because the x of 1, x of 2, and so forth are independent and identically distributed, then, and I should say, and the symmetry of the h of s of n, what we have is the expected value of x sub I times h of s of n is equal to the expected value of x of j times h of s of n, and that's for all ij elements 1, 2, all the way up to n. This can be seen, for example, when I is equal to 1 and j is equal to 2 by, okay, so I'll look at this. What the expected value of x of 1, h of S of n. I should say one more thing, I'm sorry. So in my example, when x1, x2, and so forth are all discrete random variables, well, look at it in that case. As the expected value of x of 1 times s of n. Okay, so here this is equal to the expected value of x of 1 times the sum. Well, here, let me write out this one. Okay, this s of n has n of the random variables involved that we're adding together. So x of 1, x of 2, and so forth. So if we look just at this part, this will be the sum over x1, sum over x2, the sum over x of n of x of 1 times h of x of 1 plus x of 2 plus all the way up to plus x of n, I've run out of room, times f of x of 1, x of 2, all the way up to x of n. That's the joint PMF involving x of 1 up to x of n. So it's times that. That would be equal to the sum over x of 1's, sum over x of 2's, x of 1, h x1 plus x2 plus all the way up to xn. And then due to independence, I could rewrite this as f of x1 times f of x2 all the way up to multiplication to f of xn. So that's what we do. And then but what we notice, okay, what we notice is that the x1 output values are the same as x2 output values, and f of x1 is equal to f of x2, and h of x1 all the way up, let's just say this, h of x1 plus x2 and so forth is the same thing as h of x2 plus x1 plus so forth. So I switch to x1 and x2. This is the same thing as the sum over x2, sum over x1, and here, this should have been xn. Here, let's put x2 involved with this one. Up to the sum of the xn, and I could replace this by x2, and here this is h of x2 plus x1 plus x of n, and then this is f of x1, okay, or I could put down x2 and x1 here, it doesn't matter, and I will, up to f of xn. And that, due to the independence, we can just work backwards, and we get that's the same thing as the expected value of x2 times h of s, excuse me, Sn. So they're the same. Okay? All right. So, what we were looking at was the expected value of, it was S of n h times h of S of n. And we said, well, that's the same thing as we got to the sum as n runs from 0 to infinity. So where it was the sum as I runs from 1 to n of the expected value of xi, h of Sn, small n, times the probability that n is equal to n. That's where we were. Except we said that these were all the same, so I'll make that replacement. So might as well put the expected value of x of 1, h of S of n, times probability that n equals to n. But this is one thing. Okay? It's a constant, if you will. And so it doesn't depend on I. And so there are going to be n of them. And so this is the sum, the outer sum. N runs from 0 to infinity. There will be n of these. So n times the expected value of x of 1 times h of S of n times the probability that n equals to n. That's where we are. Okay, and what we're going to do next is use the relationship that we had, so before I leave it, we're going to use the relationship that we had between the probability that m is equal to n. Remember this, the probability that in our, I'll write it up here. All right, so the probability that m is equal to n is equal to n times probability that n equal to n over the expected value of n was in the condition of the statement. And so this means that the n times the probability of n is really equal to the probability m equals to n times the expected value of n. And so that's what I'm going to do is make a replacement there. So we get, this is equal to, so it would be the sum as n runs from 0 to infinity of, it would be expected value of n times expected value of x of 1 times h of S of n times the probability that n equals to n. The expected value of n is a constant. I can pull that out. So that's equal to the expected value of n times the sum as n runs from 0 to infinity of the expected value of x of 1, h, S of n times the probability that n equals to n. I'm sorry, it shouldn't be n equals to n. It should be m equals to n. So this is m equals to n. That's what this is. Okay, now here we are going to use independence for the m. So this is the same thing. Independence for the m with the x sub the sequences of the x of 1 x of 2. To rewrite this as the sum as n runs from 0 to infinity, the expected value of x of 1 times h of S of n given m equals to n. And that's the same thing due to independence. Comes the probability that m is equal to n. But here, because we know m is equal to n, we replace that n with big M. And that's all I'm going to do in this line. So S of M, okay, and this is given, M is equal to N times the probability that M equals N. And that last part, maybe we should even keep it here for a second. Okay. This sum over the n values, that's the, I guess I could write it right here. This is going to be right. That's equal to expected value of n. This would be the expected value of, this is conditional expected value, so it's expected value of x of 1 given h of s of m given m equals to n. That's what that is. So the expected value of the conditional expected value would be nothing more, so I think I can finish it right here. Then expected value of n. So this is equal to, the second part is equal to the expected value of x of 1, h of s of m. And that's what we wanted to show. Okay. So that ends it. I'll end it there. Okay. The next thing we want to do, before I go on, we have seen this a little bit before, example of this. Remember what we just showed was that the expected value, you don't have to write this down, but the expected value of s of n, h of s of n, was equal to this. If you let h of s of n be 1, then one thing we had already stated was the expected value of the compound random variable. What it was the expected value of n times the expected value of x of 1, where this part would have been 1. That's something we've already stated. So in essence, we're looking in the compound random variable identity, something that's more generalized than what we had used earlier, shown earlier. All right. Well, the next thing we want to do is a corollary to this. So corollary says the following, excuse me, C-O-R-O-L-L-A-R. Says let S of n be a compound random variable and suppose x of 1, x of 2, so forth are positive, that's important, integer value random variables. Then in terms of notation, suppose the probability that x of I, well, let's just say probability x of 1 equals to j equals to alpha sub j. So that's what we'll denote that. With, for j being greater than 0. And m is a random variable that is independent sequences of x sub i's and satisfies that probability condition. I'll write that up. That probability condition is the one satisfied in the compound random variable identity. So it's independent, the M is, of the sequence of random variables. X1, X2, so forth, and satisfies the probability that M equals to N is the same thing as N times the probability that N equals to N over the expected value of N. Then, so here's our conclusion. The probability that S of N is equal to 0 is the same thing as the probability that N equals to 0. So we'll prove that last. And the probability that S of N is equal to, let's say, K, that's equal to 1 over K times the expected value of N times the sum as J runs from 1 to K of J alpha sub J times the probability that S of M minus 1 is equal to K minus J. Okay, so that's what we get. And this is a corollary that will be beneficial for us to use in certain examples. Okay? We'll do that during our next video. Okay, we won't prove this. So for a fixed K, so we're going to find, we're going to let h of x, our function involved in the compound random variable identity, be equal to, so one of two things. It's either 1 if x equals to k, and 0 otherwise. And note that S of n, h of S of n, well, okay, so this should be equal to one of two things. It's k. So what's h of S of n? Well, most of the time, h of something is just 0. The only time that it's not 0 is when when it's 1, and the only time it's 1 is when S of n is equal to k. So this would be 1 when S of n is equal to k, and otherwise it's 0. So it's 1 times, well, S of n, but S of n has to be k for that to be 1. So it's k or it's 0, and this is k if S of n is equal to k, and it's 0 otherwise. Okay, that's what we have. Therefore, the expected value of S of n times h of S of n would be equal to, okay, so this is an expected value of a random variable that's just only has two output values, k or 0. And so remember, it would be the sum over all of its output values, which would be just 0 or k, of those output values times the chance of getting those output values. So here it's just when you have 0 times f of 0, if you get 0 plus k times f of k. So that's the probability that this guy is equal to k. And when is that guy equal to k? That's when S of n is equal to k. All right. Now, by the compound random variable identity, the expected value of S of n, h of S of n, so what we just proved, was this was the expected value of n times the expected value of x of 1 times h of s of n. S of m. That's what we had. Okay. So, combining, we have two versions for what the expected value of s of n times h of s of n are. So this says that k times p, the probability of s of n equaling k, has got to be equal to this part. And okay. Now, we want to solve for the probability that s of n is equal to k. All right. You know, one of the things that maybe I didn't emphasize here in the identity, or in this corollary, the k that we're dealing with here is with k being greater than 0. So that we had a part when k was equal to 0, that's the probability that s of n is equal to 0, that's the probability n is equal to 0. And for all other k's, for k being bigger than 0, we have a different result. And we're working on that different result right now. So here's where we are. We're going to work with this. You see that you're going to be divided by 1 over k, and the 1 over k times the expected value of n was involved in what we said the result would be. So really we need to concentrate on this second factor here. And the way we're going to handle that is by conditioning. So this is equal to the expected value of n, and this is the expected value of the expected value of x of 1, h of s of m, given x of 1 is equal to some number j. So what is the value of x of 1? So that's equal to the expected value of n times, okay, so we're doing expected value of conditional expected value. So that is a sum over all j outputs, so j could be 1 to infinity, of the conditional expectation of x of 1, h of s of m, that's what we had, given x of 1 equals to j times the probability that x of 1 equals to j. And we have a symbolism for the probability that x of 1 is equal to j. Remember, that was the alphas of j. So this is equal to expected value of n. Okay? And then here, this is the sum over the j's. Here, this is the expected value of x of 1, h of s of m, x of 1 equaling to j, This is alpha sub j. And that's what that is. And now, here we can do a little bit work about x of 1. We know that it's j, so this is equal to the expected value of n times the sum as j runs from 1 to infinity. This is the expected value of j times h of s of m, given x of 1 is equal to j times alpha sub j. And then this j is a constant. It can be taken out of that conditional expected value. So that's equal to the expected value of n times the sum as j runs from 1 to infinity of j times the expected value of h of s of m, given x of 1 equals to j times alpha sub j. So we got to figure out about this conditional expected value. Okay. So this is equal to expected value of n times, okay, it's the sum as j runs from 1 to infinity. There is a j, and now the conditional expected value is going to be nothing more than the sum over the output values of s of m, so I'm going to call them s of m prime, their output values. This is h of s of m prime, and then it's a conditional expected value, so it's the conditional PMF of s of m prime given x, okay, this way, so 1, so this shouldn't have prime, it should be s of m. S of m prime is an output value given j, that's what we have, and here is the alpha sub j that still needs to be there. All right, that's equal to the expected value of n times the sum as j runs from 1 to infinity, okay, of j. Now, here's what I'm thinking. Remember that h of s of n prime, that's because the way we defined h, that's going to be 0 most of the time. The only time that it's not 0 is when s of n prime is equal to k. So s of n prime is equal to k. So this is going to have only one term in it. It's going to be, so this j is this j, this sum is this sum. Here's only got one term that's non-zero. What is that one non-term zero? It's when s of m is equal to k. So this is nothing more than 1 times this guy is the probability that s of m equals to k, given x of 1 equals to j times alpha sub j. So that's what that is. And the reason was as h of s prime of m equals to 0, except when s sub m prime is equal to k, and in this case, that case, h of s of m prime equals to 1. So this only has one term in it. These are all zeros except for one time. You get 1, and that's when this guy, s of m prime, was equal to k. So this is the probability that s of m is equal to k given x of 1 is equal to j. So now we've got to concentrate on that. Now, the probability that s of m equals to k given x of 1 equals to j, this is the same thing as the probability Okay, S of m is a sum, so it's a sum, if you will, as I runs from 1 to m of x sub I. If that's equal to k, okay, given x sub 1 equals to j. Okay, so we're going to put ourselves in that position. We know that x sub 1 is equal to j. Okay, so that's equal to the probability. Okay, so we know x sub 1 is equal to j, so that means that j plus the sum as I runs from 2 to m of x sub I, that whole thing is equal to k. So that's the same thing as the probability that the sum as I runs from 2 to m of x sub I equals to k minus j. These are identically distributed random variables. And so what I can do is index these. This is the same thing as the probability, if you will. So we'll let L be equal to I minus 1. So this would be the same thing as L running from 1 to m minus 1 of x sub L equals to k minus j. But that's the same thing as the probability that S of m minus 1 is equal to k minus j. That was something that was involved in the conclusion. So let's summarize where we are. So what do we have? So k times the probability that S of n equals to k, okay, is equal to, oh, there's one more thing I need to be, yeah, this is fine. Is equal to the expected value of n times the sum as j runs from 1 to infinity. Here this was j, probability that S of m equals to k given, I'm sorry, this was j times, we had the alphas of j that was there, and here we have the probability that S of m minus 1 is equal to k minus j. Okay. So, we get the result, that is the probability that S of n is equal to k, is equal to 1 over k, expected value of n. Oops, I made a mistake. I should make this one comment. It affects the answer. Okay. So here, note when j is bigger than k, bigger than k, the probability that S of m minus 1 is equal to k minus j. Really, it's just when it's bigger than k. This part is going to be equal to 0 because the x of i's involved are non-negative. They're positive integers, so you can't have a negative number here. So that's 0. So this is the same thing as k times probability that S of n is equal to k is equal to the expected value of n times the sum as j runs from 1 to only k is all you need. J, alphas of j, probability, s of m minus 1 equal to k minus j. And that's equal to, I guess, the probability that s of n equals to k is equal to 1 over k. Expected value of n, sum as j runs from 1 to k, j, alphas of j, and the probability that s of m minus 1 equals to k minus j. That's part of the result we wanted. We have one more little part to get for this corollary. Now, by definition of the x of i's, that is for n being greater than or equal to 1, the probability that s of n equals to 0 is equal to the probability sum as I runs from 1 to n of x of I equal to 0. So as long as n is bigger than or equal to 1, we're looking at this, s of n. We're looking at s of not 0. And here, that's going to be equal to 0 because the x of I, by their definition, are positive integers. So we get 0. So the probability of s of n equaling to 0, the only time s of n can be equal to 0 is when n is equal to 0. And that's the second thing we're going to prove in this corollary. So that concludes it. That concludes the corollary. There's only one more thing I want to do, and it's a fact. Here's what it says. It's a quick fact. It says, let n be a Poisson random variable with mean lambda we're going to let m be a random variable such that, or satisfying, the probability that m is equal to n is equal to n times the probability that n equals to n over the expected value of n. Then m minus 1 is a Poisson random variable with parameter lambda. Let's prove this. So we want to prove that m minus 1 is a Poisson distributive with parameter lambda. So how are we going to do that? Well, we need to look at its PMF. So I'm going to take the probability m minus 1 is equal to some number n. And I want to show that the chance of that happening is going to be e to the minus lambda lambda n over n factorial. That's what I want to show. Well, let's relate that to m. This is the same thing as probability that m is equal to n plus 1. But I know something about that. That's equal to, by the conditions on M, that's the same thing, n plus 1 times the probability that n is equal to n plus 1 over, here would be the expected value of n. But I know the expected value of n, it's lambda. So this is n plus 1, and the probability of n equaling n, well, n itself was Poisson distributed, so this will be e to the minus lambda, lambda to the n plus 1, all that over, let's probably go high, all that over n plus 1 factorial. This n plus 1 here and this n plus 1 factorial have some cancellation, and so we're left with e to the minus lambda, lambda to the n plus 1. N plus 1, one of these, the only n plus 1 there, canceled, we're left with n factorial over, this is all over lambda. This lambda here cancels with that lambda, we're left with e to the minus lambda, lambda to the n, over n factorial. That is the PMF of a Poisson distributed random variable, so m minus 1 is a Poisson random variable with parameter lambda. And that concludes this proof. And that concludes all I wanted to do today in this lecture. Thank you very much for your time and patience.